Well, welcome to another RDWorks Learning Lab. I would suggest that those of you with a weak bladder turn the sound down for a little while. Now that's not a good idea, is it? Because you won't be able to hear what I'm talking about. What I'm going to do today is some little demonstrations of the strange characteristics, puzzling characteristics of acrylic. Now acrylic is an absolutely amazing material for working with our CO2 laser. It has some really phenomenal properties which people tend to misunderstand. Here I've got my little red laser pointer, and what I'm going to do, I'm going to shine it through the water. As you can clearly see, this is a curved beam of water. And here I've got a straight beam of light. And what I'm going to do is shine the light through here, and you can see where it is on that piece of masking tape. And now I'm going to send it right into the mouth of the beam of water. The light travels down the inside of the water there, but it can't escape because there's a different density between the water and the air on the outside of the water. So you get complete internal reflection, and the beam carries on moving down the inside of the pipe. Even though the pipe is curved, you get internal reflections, and you can see that right down at the end there. We've got the light being transmitted round corners. The reason I'm showing you this is because this mechanism also occurs with our invisible light when we fire it into acrylic. Here we are at the machine, and what I'm just going to do is to set you a little bit of a thinking exercise. In this machine I have got a 1.5 inch lens. Now a 1.5 inch lens, as you know, is a very short focus lens, and basically the beam does something like this. It comes in very quickly to a very small waist there, and we've often spoken about this as being the spot size, the smallest possible focal point that we can get with a 1.5 lens, which is a 1.5 inch lens, which is around about 0.075 of a millimetre. Okay, now that's not important today. What we're more interested in is what happens up and down from this point. We only get a very short focal distance here, where what they call the working distance, and it's only less than 1 millimetre above and below the spot size point, the focal point. In fact, it's a lot less than 1 millimetre. But again, that's of interest only, but what we're going to see today is something a lot more interesting than that. After this fairly parallel area here, we get a fairly rapid expansion of the beam, and the energy density, and I've talked about this before, the energy density can best be described with this pen. Now I can jam the end of that onto my hand very, very hard. Do you think I'm going to be stupid enough to do the same thing with that end? Of course I'm not, because we've got an energy amplification taking place there, because the energy is amplified right down to a sharp point. And that's basically what happens here. The energy density here is like the end of this pen. It's fairly low, and it can't do much, and this is the critical word that I like to use. You can't damage the material much with low energy density. You have to have high energy density, where the energy is concentrated into a small area before you can do damage to the material. So consequently, we've got this point here where we're going to fire the beam at a block of acrylic. There we go. We've got a block of acrylic. Now, what I really want you to do is to try and guess. First of all, how far you think this 1.5 inch lens with 60 watts of energy just here. It's focused down into a very small area and it's very, very high energy density at that point there. So my question is, what do you expect to see when I fire the beam into this block? Do we expect to see it spreading out as per this picture so that we can see the shape of the beam? I'll tell you what we'll do. Let's fire the beam into it from the correct focal distance at the surface. In other words, I'm going to put the spot size on the surface, the correct focal distance, and we'll fire it in and we'll see what happens. As you can see, this block is 80 millimeters tall. So how far do you think we should be able to fire the beam into that block with 60 watts and a 1.5 inch lens? Because bear in mind, the energy density drops off very, very quickly. Well, write your answer on a piece of paper and put it in a sealed envelope. Don't look at it until afterwards, and then you'll see whether you were right or wrong. Okay, now you've got a front row seat. I'm going to do this twice because the first time you'll be so amazed you won't actually be able to watch what's going on. I'm going to put my finger on the pulse button and I'm going to hold it. And your first observation of that result is? Well, I certainly didn't see any major splaying of the bore because of the way in which the laser beam has grown after it starts to defocus. Look at this large section here where it's virtually parallel. We get a little bit of growth just at the top here, but then it runs parallel all the way down. But that is substantially bigger than the 0.075 focus point. So what on earth is going on? This is 80 mil tall and we've gone in somewhere in the region of about 65 millimeters. Now that doesn't mean to say I can produce a 65 millimeter cut with this 1.5 inch lens, which looks as though it should be possible. I'd have to be going very, very, very slow. But what's actually happening, if you watch in here, you'll see the next time that I do it, you'll see all sorts of like flow lines happening down here. It's almost like liquid acrylic being blown down here. It's scouring the outside of the surface with hot gases, and if we look down at the bottom here we can see all sorts of vortex flows taking place. We've got swirls, and that shows us that there's something really strange about the gas dynamics that's taking place at the bottom of this tube. But what I'm really trying to demonstrate to you here is that we've got the water pipe effect. Our beam is continuously bouncing off the inside of the bore here, and it's getting further and further down. The power is reaching right down to the bottom here by reflection. Quite staggering for a 1.5 inch lens. Now with a 2 inch lens I might be able to get nearly to the bottom, and we will probably try a 2 inch lens in a minute just to see the difference. But what I'm going to do is repeat this, and you can watch it growing again, and you'll see all the gas dynamics and the fluid dynamics taking place inside that tube. Keep trying to veer off. Spiral flows, you can see. I think it's trying to find its way out the front here because I can see a little bit of debris and smoke coming out here. Yes, it has broken. It has just broken through the surface there. So we'll just run the same thing a little bit further back. You can see things happening in the bottom of that. Can you see the spiral flows taking place in the bottom there? Okay, now one of the arguments that has often been raised is that you can get a little bit more depth of cut if you lower the focus point into the job. Well, let's just try that, should we? That's around about 2 millimeters away, so I've lowered the focus point by about 3 millimeters. And let's see what the result is now. I'm struggling to get there. Yeah, I've dropped the neck a little bit, as you can see. But the cut depth isn't quite as deep. Let's change over to a 2-inch lens and see what effect we get. 19 millimeters. There we go, 19 mil. So that's the correct setting distance for a 2-inch lens. Right, there we go. Run out of steam. But I think if you look carefully, we can see the heating effect. You can see the heat zone around the cut. Now that's a 2-inch lens, and you can clearly see the scroll marks in there, much the same sort of gas dynamics. Doesn't seem to make a lot of difference to the depth. Now we could try and close the gap up now quite a lot. 7 millimeters. That's 12 millimeters into the material. And that bottom one is the 2-inch lens. Right at the left-hand edge of the cut, you can see the size of the beam as it enters the material, but then it gets focused down. See, this is an excellent example of the way in which the material is acting like a light pipe, and it's just throwing the power right down to the bottom of the cut. It's not very accurate, as you can see, because it keeps veering off and doing all sorts of things with the gases. But the gases are the things that are scouring the side and making it bigger than the beam. So you've got no control over size, but it is quite interesting to note the way in which that beam has now gone down to something in the region of about 70 millimeters, 65 to 70 millimeters. I mean, would you have imagined you could get a cut like that? But the way in which this beam is scouring the inside of this tube, and you can see the way, you can see the fluid flow down inside there with the way in which the gas is flowing around inside there. It's quite fascinating, because that also helps to explain one of the reasons why we get these striations on the edge of our material. Now, we've seen that when we punch a hole in the acrylic, that's the beam, but round the outside of that beam there is a gas pocket which is actually cutting bigger than the beam itself. We've got to remember that what we're firing at this material is a beam of light. It's light energy, and it's not until that light energy gets absorbed into a surface that it changes into heat, and that heat is the thing that does the damage. Now in the case of acrylic, the heat actually evaporates the material instantly, producing a hole. So the hole is actually bigger than the beam, and consequently the actual gas that's in here is not as absorbent of the energy as the solid acrylic is. So consequently we've got solid acrylic all the way around here, and we've got a little gas pocket around the beam. Now the beam is moving at a steady rate in this direction, and so the beam now runs across the pocket and it can't do anything because there's nothing there to cut. There's no solid material for the light energy to be absorbed and converted into heat. So it's only when it hits this solid material that's here outside the gas zone that it starts to heat up the solid material again, and as it heats up this solid material it produces another gas cloud around the outside of it. And so this is the situation that carries on. The beam is going on steadily at a steady rate, but it's not producing a solid single cut. It's producing an intermittent cut as it jumps across this gas cloud and then hits another piece of solid material, producing another gas cloud, jumps across the gas cloud, hits another piece of solid material and produces another gas cloud. And look, here are the marks, the striations. It's the joining up of these spheres of influence, these circular patterns, that's actually causing the striations. Now I hope that the demonstration in that solid block of material has shown you some of the strange things that can go on with the laser beam and acrylic. Acrylic is a very special material. As soon as the light energy hits the surface, it gets absorbed, and it gets absorbed directly proportional to the density, the energy density. So consequently, when we do a mode burn, which if you remember was where we fire the beam at a block of acrylic, the block of acrylic produces a shape in it which looks like that. And here we've got lots of examples of that. These are mode burns. And what that shows us is there's more light energy being absorbed in the center of the cut than there is on the outside of the cut. This is the point that I keep making to you, that the energy density across our beam is not uniform. We've got a very, very high energy level in the center of the beam, and it drops off, supposedly, if the beam is manufactured correctly, in what they call a Gaussian shaped curve, where probably something like 80% of the power is contained in less than 50% of the overall diameter. But there is energy right out to the edge, but not much. Now when we're cutting, we never actually encounter this situation that we've got here. This situation that we see here is because we have let the laser beam stay on for a huge amount of time. In reality, you never get this effect when you're cutting. What tends to happen is when you're cutting, instead of a cut that looks straight like that, you might say, well, because the beam is shaped like this, you would expect to get a cut that looks like this if you drop the beam halfway into the material, or like this if you have the beam sitting on the top of the material. But to be honest, in reality, you'll get the opposite of what you think here. If you sit the beam on the surface, what you'll get maximum sphere of influence of the heat, and it will get less as it passes through the material. So this high density area here will produce a lot more heat around it, and as the energy density drops off, so the heating effect will get less, and that's why you are limited with your cut when you're moving through at a speed. That's not the same demonstration that I've just given you where we're holding the beam still. This is a dynamic situation, and what I've just demonstrated to you is a static situation. So as I said, acrylic is an absolutely fascinating material with all sorts of characteristics which you only with practice, if you're using acrylic all day every day, you may already be familiar with all these properties. But for those that haven't played with acrylic very much, then there's a whole new world here for you to explore. Well, it's time for me to go and top up my tank, so I need to say cheerio for now, and I'll catch up with you in the next session.